Hi everybody. In this video we are going to discuss superposition in AC circuits. So circuits with AC voltage supplies, AC current supplies and complex impedances. If you haven't studied the video about superposition in general, please do because that video discusses the basics about superposition. So, well, what was it all about? Superposition considers every source in a circuit independently. So every voltage source and every current source independently and looks to the contribution of that independent voltage or current source. When we do that, we replace the remaining current sources by open circuits. So the circle of this current source vanishes and all the other voltage sources are short circuits. So also in this case, the circle vanishes, so we can see that the voltage source is replaced by a short circuit. Well, that's the basic about superposition. Now let's look to a complex network in which we have two AC voltages put over here, and we have several complex impedances consisting of a real part and an imaginary part. So this could be a resistor and an inductor in series. And we have two resistors also in this circuit. And we are going to calculate the voltage at this point A, with respect to this grounding symbol. So the voltage across this impedance, point A towards the grounding point. And what we are going to do is we are going to look into the contribution of this voltage source, and then we neglect the contribution of that voltage source, so replace that by a short circuit. And the second step, we are going to look to this contribution, and we replace this voltage source by a short circuit, and then we add up all two voltages which we have calculated over here, and then we come to the end solution. So let's do it. So let's start off with replacing that voltage source by short circuit, which leaves us with this network in which we have only one voltage source left. Well, the first thing we can do is make this circuit diagram somewhat less complex, so somewhat easier. And we can do that because we see here two impedances in series. And when we have a series connection, we can replace this by one series impedance by adding the real parts of these impedances, which is 10 ohms and zero point 0 ohms together, and we add up the imaginary parts of these impedances, which is 0 ohms over here and zero point 0.5 ohms over here, and then we have one series impedance, and we can do that the same in the upper part of the circuit with the same resistor and the same complex impedance parts. So when we have done that, we have two new complex impedances over here with the real part 10.5 ohms and the imaginary part 0.5 j ohm, which is also the situation over here. So when we have this, we can do the second step, which makes life much more easier because we see here two impedances in parallel. So we can replace these two impedances by one impedance, and we can do that in the following way. We can say, well, 1 over the replacement impedance is 1 over this impedance plus 1 over that impedance. And then we can calculate a replacement impedance. Because these are only two impedances, we can also say the replacement impedance is this impedance multiplied with that impedance divided by the sum of this impedance and that impedance. And then we also get a complex impedance. But this complex impedance has a numerator and a denominator. And when we want to write it down in a complex form of only one real part and one imaginary part, we have to multiply the denominator by the complex conjugated. And that is the same real part with the negative imaginary part. And when we do all these calculations, which I'm not going to do in this video, then we come up with one new impedance, which is this impedance, which has a real part, which is equal to 121 over 244, and an imaginary part 100 and 11 divided by 244 times J, of course, because it's imaginary part. So now we have a rather easy circuit diagram with one impedance over here and one impedance over there. And remember, we want to calculate the voltage at point A with respect to this grounding symbol, so with respect to this point. So now we can use the voltage division rule, which says that the voltage at this point, with respect to the ground over here, is equal to this impedance divided by the summation of that impedance plus this impedance. So it's and then multiplied, of course, by the voltage over here. So the voltage at point A, UA, is Z1 divided by Z1 plus Z2, and that multiplied with this voltage of 220 volt. And when we do that, we see it over here, we get this as a solution. Well, UA is 10.6 volt, which is the real part, plus 8.2 times J volt, which is the imaginary part. So also the voltage is a complex voltage written over here. So, well, this was the first part, and now we can do the same with the second part. So in that second part, we are going to neglect this voltage source, replace that by a short circuit, and then we take into account the other voltage supply. So then we have this situation. So this voltage source has been replaced by a short circuit. And what you see now is that this circuit diagram looks the same as the circuit diagram which we had before, because these values over here are the same and these values are the same. So we can do the same stuff in making this circuit diagram somewhat more easier. But first of all, let's start off with this voltage, which is a voltage supply with a phase angle of 180 degrees. So this is a sine wave with a phase angle of 180 degrees. And when you look to a sine wave with a phase shift of 180 degrees, we can see that that is the same as a sine wave with a minus in front of it, so a negative sine wave. Well, draw it at a piece of paper. You see that when you shift a normal sine wave 180 degrees, then the remaining sine wave starts with a negative a part of the sine wave. So we can replace this sine wave by the same sine wave of 220 volt amplitude, but with a reverse polarity. So the minus over here and the plus over there. So when we do that, we have an easier circuit diagram again, because now we have similar circuit diagram which we had in part 1. So what are we going to do? This is my voltage source, which I take into account, which is nice and easy because the minus is related to the ground symbol over here. We are going to replace these two impedances by one impedance by adding them up. We are doing the same over here. And when we have done that, we can, well, it was a bit too fast. We can replace this series impedance and that impedance by using the parallel formula, which says that 1 over the total replacement impedance is 1 over this impedance plus 1 over that impedance. And when we do that, we have the same as we saw in part number 1. We have a Z1 over here, which is this expression, and we have a Z2 over here. And we can do the voltage division rule. We can apply that, and then we have the voltage at point A with respect to the ground over here. And that gives us the same voltage as what we calculated in part 1, which is 10.6 plus 8.2 J volt. So that was because this is a circuit which has the same parts on the upper side and the lower side. So there's a kind of symmetry in this circuit. And now we can look to the total voltage on point number 1, which is the solution of part number 1 and the solution of part number 2. So it's 2 times this voltage, the real part, and 2 times that voltage, imaginary part, which brings us the following. The end solution as UA is the summation of both parts, which is 21.2 volt plus 16.4 times J volt, which has a real part and imaginary part, as we can see over here. So what we have seen is that for complex circuits with AC voltages, all the rules for superposition still apply, and that makes life still much more easier to calculate a voltage or a current at a specific spot. Thank you for watching, and I see you next time.